Alright, so in this video what we are going to do is cover a couple of important tests for convergence or divergence of a series. These tests are called the root and the ratio test. Okay, so let me begin with the root test. Right, so the statement of the root test is as follows. Given a series xn, define this number, define alpha to be the lim sup of absolute value of xn raised to 1 by n, right? And in terms of alpha, the root test goes as follows. If alpha is less than 1, then series converges absolutely. On the other hand, if alpha is greater than 1, the series diverges. And finally, if alpha is equal to 1, then it turns out the test is inconclusive. Okay, so that's the statement of the root test. So given any series, define alpha to be the lim sup of the nth root of absolute value of xn. Okay, and depending, now clearly this alpha is the lim sup of a non-negative sequence. Therefore alpha has to be some non-negative real value or it has to be infinity. Right? Depending on the range of the value of alpha, you can say something about the series either converging or diverging. If alpha is less than 1, the series converges absolutely. If it's greater than 1, the series diverges. And if alpha is equal to 1, if you're at the boundary between these two, it turns out the test is inconclusive. In other words, you can come up with examples of series where alpha is 1 and the series itself is convergent. Similarly, you can also come up with examples where alpha is 1 and the sequences and the series is divergent, and we will give such examples in a bit. Okay, now one thing to note before we get into the proof of the root test statement is what is the intuition for this particular definition of alpha. So it turns out that the root test is primarily suited for those series where the summends have some sort of exponential decay associated with them. Okay, so in particular, suppose that you're looking at a series of the form where xn is equal to a raised to n, right? In that case, your absolute value of xn raised to 1 by n would in fact be mod a, right? And indeed, you already know that if mod a is less than 1, then summation a raised to n converges. If mod a is greater than 1, then summation a raised to n would in fact diverge, right? So it's not surprising that the statement of the root test actually does hold, right? So at least in the case where xn is a pure exponential of the form a raised to a, it's clear that the statement of the root test holds, at least the first two, right? Why in the boundary case when alpha is equal to 1 the test is inconclusive may not be apparent from this connection. We will see examples to that effect in a bit. Okay, but yeah, the moral of the story I'm trying to convey here is that the root test is in fact primarily designed for those scenarios where the summends have a certain dominant exponential uh, behavior associated with them. Alright, so I'll come back to this later. Now let's get to the proof. Right, now there are three parts to the proof, of course. The case where alpha is less than 1, the case where alpha is greater than 1, and then finally the inconclusive part. So let me start with the first part where alpha is in fact less than 1. Now in this case, the scenario is that you have 1 here, you have alpha here. I can find a number beta which is between alpha and 1, right? For example, beta could just be the midpoint of alpha and 1. So what I'm going to do is pick some beta which is in the interval from alpha to 1. Okay, now why am I doing this? Well, this beta has the property that it is a number that is larger than the limb sup of absolute value of xn raised to 1 by n. However, it is also less than 1. Okay, now because beta is a number that is greater than the limb sup of the sequence mod xn raised to 1 by n, beyond a certain point the entries of the sequence must be less than beta, right? So the fact that beta is more than alpha implies that there exists, let's say, some n naught in the naturals such that mod xn raised to 1 by n is in fact less than or equal to beta for all n greater than equal to n naught, right? What that implies is that if you look at absolute value of xn, that's in fact less than or equal to beta raised to n for all n greater than equal to n naught. And now we are done, because from the comparison test, since summation beta raised to n converges, well, summation xn converges absolutely. Since summation beta raised to n converges, summation xn converges absolutely. Right, so that's it. So an elementary application of the comparison test in fact shows that essentially xn is bounded above by an exponentially decaying sequence, or the absolute value of xn is bounded above by an exponentially decaying sequence, and so you're done. Comparison test tells you that you have absolute convergence. Now let's move on to part 2, where alpha is actually more than 1. Right? Now if alpha is more than 1, again I'm going to pick a number beta between 1 and alpha. So 1 is here, alpha is here. I'm going to pick a number beta which is in fact now more than 1 but less than alpha. Okay, now what is the feature of this beta? Yes, it is larger than 1 and it is a number which is smaller than the limb sup. Okay, now what is the consequence of this? It is no longer true that every element of the sequence mod xn raised to 1 by n does not exceed beta beyond a certain threshold. However, you are guaranteed that there exists a subsequence along which this behavior holds. So let me write this down and then I'll kind of, if it's not clear, I'll justify why this is in a bit. There exists a subsequence x and k, and let's say a natural number k, such that along this subsequence is in fact greater than or equal to beta for all k greater than capital K. Okay, now why is this true? Well, it follows from the fact that since alpha is in fact the limit superior of absolute value of xn raised to 1 by n, there exists a subsequence of the sequence which in fact converges to alpha, or at least has a limit alpha. Again, I'm not assuming that alpha is real valued. This case also subsumes alpha equals infinity, right? Since there exists a subsequence x and k that tends to alpha, clearly because beta is less than alpha, along that subsequence after a certain threshold, the elements of the subsequence are going to be greater than or equal to beta because beta is less than alpha, right? So this follows by just constructing the subsequence x and k in such a way that as k goes to infinity, x and k, rather absolute value of x and k raised to 1 by nk actually tends to alpha. If the fact that it tends to alpha implies that the elements of that subsequence will in fact exceed beta beyond a certain point. That point is what we are calling capital K. Okay, now a consequence of what we have written above is that absolute value of x and k is in fact greater than or equal to beta raised to nk, also for all k greater than equal to k, right? Well, the fact that beta is greater than 1 implies that along this subsequence, absolute value of x and k actually tends to infinity. Okay, which means, yeah, so along this subsequence, x and k in absolute value has to tend to infinity because it's in fact lower bounded by beta raised to nk, where beta is more than 1. Right? And this itself implies that the sequence xn itself, because after all absolute value of x and k is in fact a subsequence of the sequence absolute value of xn, right? This sequence does not in fact tend to 0. And the fact that it does not tend to 0 implies that summation xn diverges. Because remember, for any convergent sequence, you have that xn tends to 0. We proved this earlier. So the fact that xn does not tend to 0 implies that the series must diverge. Right? So that concludes part 2. For part 3, all I have to do is give you an example of a series where alpha is equal to 1 and the series is actually convergent, and similarly an example where the series diverges. So you just have to consider 2 simple cases. Summation 1 by n, summation 1 by n square. Okay, I leave it to you to check that in fact in both cases alpha is equal to 1. However, we have already shown that summation 1 by, so alpha is 1 for both of these series. However, we have already shown that summation 1 by n diverges, whereas summation 1 by n square converges. Right? So that shows that if alpha is equal to 1, the test is in fact inconclusive. Okay? And again, you can see that the place where the test is actually inconclusive, the examples where the test is inconclusive, is precisely those places where the summands don't have a dominant exponential behavior in their decay. In the both examples that I gave, summation 1 by n and summation 1 by n square, the summands actually have a power law or polynomial-ish decay, right? And it is precisely in those cases that the root test is in fact inconclusive. All right. So that gets us to the end of the root test. Next, we are going to move on to the second of the test, which is called the ratio test. So the statement of the ratio test is as follows. So now consider the series summation xn with non-zero entries. Non-zero terms. What I mean is that these xn's are non-zero, and it will be apparent in a bit why I need the assumption that the xn's are non-zero. If lim sup of absolute value xn plus 1 by xn, if this is less than 1, implies the series converges absolutely. Okay. The second part of the ratio test is that the lim inf of the same sequence exceeds 1, then the series diverges. Right? So the first case is where the lim sup of a certain sequence is less than 1. The second case is where the lim inf is more than 1. The third and final case would of course be where the lim sup and the lim inf are on either side of 1. So lim inf in this case, the test is inconclusive. Right? So once having stated the test, it's clear why it's called the ratio test, because you're looking at the ratio of the successive summands of your series, right? You're looking at the ratio of xn plus 1 by xn, and if the absolute value of that, based on the limiting behavior of that sequence, you are basically concluding either that the series converges or the series diverges, right? Of course, unless the lim sup and the lim inf are on either side of 1, in which case, well, the test is inconclusive, right? To again, I should note that, so we will make some comments on the relationship between the root test and the ratio test in a bit, but I should note that the ratio test is in fact also primarily suited to those series where the dominant behavior of the summands is exponential. Okay, to see this, you can check that if xn is equal to, again, of the form a raised to n, note that absolute value of xn plus 1 by xn is in fact also mod a, right? And again, in this case, as a sanity check, you can conclude that if this a was less than 1, when we know that the series summation xn converges, and converges absolutely. You also know that if a in absolute value is more than 1, then we know that the series diverges, right? Because it's a divergent geometric sum, right? So again, keep this in mind. So this is basically, yeah, a quick sanity check, and it kind of sees that, you know, both the ratio test and the root test are basically trying to address series where the dominant behavior, they're not exactly exponential, of course, in which case, you know, you don't need to devise a test for this, but you will, when we do the examples on this, it will become apparent that you need the dominant behavior to be exponential for these tests to be conclusive. All right, so now let's get to the proof. So the way we are going to prove this, the statement of the ratio test is itself via an intermediate result, which is, you know, useful in its own right. Right. So I'm going to state this, this as a separate theorem, and from this theorem, the statement of the ratio test will follow. Right, and our strategy is going to be to basically piggyback on the proof that we have already done for the root test. So we will prove the ratio test via the root test, via the, using the following theorem. Consider a sequence of non-zero terms let's say the sequence is xn. Okay, then the following inequalities hold. Lim inf Okay, so this string of inequalities we will prove to be true for any sequence xn of non-zero terms. Again, the fact, you need the fact that these are non-zero, well, because I have these, I'm taking these ratios, right, of xn plus 1 by xn. I don't want these ratios to become undefined. That's the reason to enforce that the sequence is non-zero. Okay, so we will prove this. There are three inequalities here. Let's call it inequality A, inequality B, inequality C. So you will see that the inequalities in fact relate the objects that are involved between the root test and the ratio test, right? So this, the leftmost number here is in fact involved in the ratio test, right? Because it's just the lim inf of xn plus 1 by xn absolute value. That, according to this theorem, is less than equal to the lim inf of mod xn raised to 1 by n, which obviously is less than equal to the lim sup of the same sequence, but this is exactly what we called alpha from the root test. Right, and finally I have the rightmost number, which is the largest in the string of inequalities, in fact also shows up in the ratio test. Okay, so again, before we get into the proof of this theorem itself, I want to convince you that once this theorem is proved, the statement of the ratio test is proved for free. Okay, now why is that? Let's look at the first statement of the ratio test. The first statement of the ratio test is the lim sup, which is this object, the one that I've written on the rightmost. If that is less than 1, right? Given the string of inequalities, if the lim sup of mod xn plus 1 by xn is in fact less than 1, it follows that alpha is also less than 1, and so therefore, by the statement of the root test, which we have already proved, the series converges absolutely, right? So I can piggyback on the statement of the root test to prove the ratio test. Similarly, if you look at the second statement, when I'm now looking at the leftmost fellow out here, right? The second part is that if that lim inf of mod xn plus 1 by xn is more than 1, well, in that case, by the same string of inequalities, it follows that alpha is also more than 1, which in which case, again, the root test implies that the series diverges. Right? And finally, the fact that when the lim sup and the lim inf are on either side, the test is inconclusive, follows by just demonstrating an example where that is the case. Right? And if you can go back, you will be able to check that the very same examples that we gave for the root test being inconclusive also applied to the ratio test. So that doesn't require a separate argument. Okay, so with this, it should be clear that the statement of the ratio test follows once this theorem has been proved. Right, so what I'm going to do next is, and this theorem is something that has independent applicability, right? So we will see a few examples, particularly in the upcoming homework, where we will be able to use this this result independently of its connection to the root test and the ratio test. All right, so now let us go about proving this. Now, the middle inequality B is trivial. There's nothing to prove. It's just that the lim inf of a certain sequence is less than or equal to the lim sup of the same sequence, right? So B is trivial. So essentially all that remains is to prove the inequalities A and C, right? As you should expect, proving one in fact shows that the other is also true, via basically an elementary argument along similar lines. So what I'm going to do is simply focus on C, right? So I'll prove C, A will follow similarly. So we prove C, the proof of A is on similar lines. Right? So now this along similar lines is an argument I get to make but not you. So when I say it's along similar lines, what I'm implicitly saying, it's an exercise for you to go and show that it actually holds. All right. So good. So this is what we want to prove. So we want to prove that lim sup of absolute value of xn raised to 1 by n is less than or equal to the lim sup of, okay, this one we have already called alpha, this number let's call it L. So I want to prove that alpha is in fact less than or equal to L. Okay, so here is how the proof is going to work. If L is infinity, this is trivial. Right? If L is infinity, obviously alpha is less than or equal to L, irrespective of what alpha is. So we are done. So therefore, what matters is to consider the case where L is real valued. So let me do that on the next page. Okay. Yeah, maybe it's worth reminding you what these things are. Alpha is the lim sup of xn raised to 1 by n, and L is in fact the lim sup of mod xn plus 1 by xn, right? And I want to show that alpha is less than or equal to L. Okay, so suppose that L is real valued, then for epsilon greater than 0, there exists an n naught such that right? So the fact that L is the limb soup of a certain sequence implies that if you take any number which is more than L, in this case that's L plus epsilon, then beyond a certain point the sequence is going to be less than or equal to L plus epsilon. Okay, this follows from the fact that L is in fact the limb soup of the sequence mod xn plus 1 by xn, right? What that implies is that mod xn plus 1 is less than equal to L plus epsilon times mod xn. Now, if you apply that inductively, you can actually easily come to the following conclusion. For n greater than equal to n naught, absolute value of xn is in fact less than or equal to L plus epsilon raised to n minus n naught absolute value of xn naught. Okay, this is just obtained by inductively applying the previous inequality, right? I leave that for you to check, which implies again that for n greater than equal to n naught, absolute value of xn is in fact less than or equal to some constant, which let's call it xn naught into L plus epsilon raised to minus n naught. This entire thing, let's call it a into L plus epsilon raised to n. What we have really done is shown that if L is in fact the limb soup of mod xn plus 1 by xn, then beyond a certain point, the sequence absolute value of xn is upper bounded by some constant times L plus epsilon raised to n. In other words, we have provided an exponential upper bound on absolute value of xn. Okay, now therefore, if you now take the nth root of this, that's clearly less than equal to a raised to 1 by n times L plus epsilon. Okay, again this is only true for n greater than equal to n naught, right? Well, now I am almost done, because since xn raised to 1 by n is less than equal to a raised to 1 by n into L plus epsilon, the limb soup of the former sequence is less than or equal to the limb soup of the latter sequence, right? So the limb soup of absolute value of xn raised to 1 by n is less than or equal to the limb soup of this fellow, but the limb soup of this fellow is in fact just L plus epsilon, because that is actually a convergent sequence, right? Because a raised to 1 by n tends to 1. And that's done. So this limb soup on the left hand side is in fact exactly what we have been calling alpha, right? So what we have learnt is that that alpha is less than equal to L plus epsilon for every positive epsilon. So since alpha is less than or equal to L plus epsilon for all positive epsilon, alpha must be less than equal to L, right? And that completes the proof, right? So this proves that result, that that string of inequalities holds, which in turn, remember, implies the ratio test. So effectively we have proved both the root test and the ratio test. Okay. However, what I'd like to do is restate that inequality here and give you a couple of more takeaways in terms of the relationship between the root test and the ratio test. So recall that this is what we have just proved, right? That the limb inf mod xn plus 1 by xn is less than or equal to the limb inf of mod xn raised to 1 by n, which is less than the limb soup of the same fellow, which in turn is less than equal to the limb soup of okay. So this is what we just proved, and there are two conclusions that I want to draw from here. The first conclusion, I told you, remember, that both the ratio test and the root test are somewhat engineered to work with series where the dominant behavior of the summons is exponential, Okay, so now the question is, well, can I say something about how these two compare? Can I say that one of these tests is more general than the other? So it turns out that this result in fact tells you that. If you think about it, we proved the ratio test by invoking the root test, right? So therefore we know already from the proof that whenever the ratio test works, the root test also works, right? So that itself should tell you that the root test is more powerful than the ratio test. Another way of seeing that is that if the root test is inconclusive, right? When is the root test inconclusive? When this fellow is equal to 1. But if this fellow is equal to 1, then clearly the lim sup and the lim inf of mod xn plus 1 by xn are in fact on either side of 1. So if the root test is inconclusive, so is the ratio test. Right? So that also tells you that the root test is more powerful than the ratio test. The the negation of this very claim is that whenever the ratio test is conclusive, the root test is also conclusive, right? So again, that also implies the same thing, that the root test is more general, more powerful. To show that this is in some sense strictly true, you need to basically come up with an example where the root test is conclusive but the ratio test is inconclusive. So I mean, we'll give an example of this sort very shortly. But if you think about it, what do you want to happen? Well, you want this fellow alpha to either be more than 1 or less than 1. So suppose you want alpha to be less than 1. That would imply that the root test would tell you that this is the series is in fact convergent, but you can engineer the series in such a way that this lim sup ends up being more than 1, right? In that case, well, the ratio test would be inconclusive, but the root test would be conclusive. And that example would demonstrate that the root test is in some strict sense more general than the ratio test, right? But the reason we study both is because in some cases the ratio test is just easier to apply, right? This is one takeaway that I wanted to share. And another is that if your series is such that xn plus 1 by xn, right, this sequence actually tends to 1, right? Now if this fellow tends to 1, what that means is that the lim sup and lim inf are equal to 1. So the endpoints of this entire string of inequalities are both equal to 1, which implies that everybody is equal to 1. Alpha is equal to 1, the lim sup is equal to 1, the lim inf of mod xn plus 1 by xn is equal to 1. So in this case, both tests are in fact inconclusive. Right? And you can check that in fact those examples of the form summation 1 by n, summation 1 by n square and so on, those actually fall in this category where both the tests are in fact inconclusive because there isn't really a dominant exponential behavior to catch. Okay, so now what I'm going to do before we conclude is to give a string of examples of the ratio test and the root test. Okay, the first one we'll consider is summation minus 1 by 3 raised to n. Okay, so in this case you can check that according to the root test your alpha would be 1 by 3. According to the ratio test, well, mod xn plus 1 by mod xn would in fact be 1 by 3. Both of these numbers being less than 1 implies that the series in fact converges absolutely. Absolute convergence, right? This follows from both tests, and again this is not this is very obvious because of the fact that the summands are in fact exponentially decaying, right? I mean in absolute value at least. So this is of the form summation a raised to n where a is minus 1 by 3. So of course I expect both tests to give you absolute convergence, right? However, you can also have examples where the dominant behavior is, the dominant behavior is exponential but not not perfectly exponential, right? So for example, consider a series of the form summation n raised to 3 by n. Okay, in this case there is an exponential component, the 1 by 3 raised to n factor, but there's also the n, so there's a polynomial thing, right? In this case you can check again that both tests imply absolute convergence. Right. I'm not going through the steps because I think they're easy for you to check. You leverage the fact that we have already proved that n raised to 1 by n tends to 1 to basically show that that in fact alpha is equal to 1 by 3 once again in this example. The polynomial factor basically doesn't play a role in determining the convergence or divergence of the sequence because the polynomial is multiplied by a decaying exponential which dominates, right? Which again tells you why these two tests are conclusive. Okay. To give you an example of tests where both are inconclusive, well, these are examples of the form 1 by n raised to p, right? So in these cases, so this p is greater than 0, right? For all such cases where summation 1 by n, summation 1 by n square are special cases, in all of these cases you will in fact have both tests be inconclusive. Right? And why? Because the behavior of the summons is polynomial rather than exponential, right? And so, yeah, neither of these tests can really catch it, but we already have the machinery. We have already seen other ways of showing under what conditions summation 1 by n raised to p converges and under what conditions it diverges. So we know the answer, except that the ratio and the root test do not tell us the answer. Next, let's do one more example where in fact these tests are inconclusive, right? This is again motivated by the same example that I've done just before. Consider something like summation n divided by, let's say, n squared plus 3. Okay, consider a series like this. Now in this case, again both tests are inconclusive. Why? Because if you look at, if you call this xn, you can check that xn plus 1 by xn actually tends to 1, right? Implying that both tests are inconclusive. Right? Again, polynomial behavior, right? But again, if you stare at this for a bit, you will see that n divided by n squared plus 3 has a dominant 1 by n type behavior. So you should expect this series to diverge, and it's actually not that hard to show by a direct application of the comparison test. So in particular, summation n by n squared plus 3 is clearly going to be greater than or equal to summation n. So n squared plus 3 is in fact upper bounded by 4n square, right? Which is 1 by 4 times summation 1 by n, which is infinity. Okay, so a direct application of the comparison test shows that in fact this fellow diverges, but both the ratio test and the root test are in fact inconclusive, right? So the final example I want to give is to basically demonstrate why the root test is in fact more powerful than the ratio test. So I'm going to give you an example of a series where the root test conclusively shows that it converges, but the ratio test is inconclusive. Okay, and again, you can, if you understand how these tests work, it'll be easy to see how this particular example has been engineered. So the example is as follows. It's summation 2 raised to minus 1 raised to n minus n. Let's say 0 to infinity. So if you look at the summons here, it is 2 raised to minus n times 2 raised to minus 1 raised to n. So what's happening here? The dominant behavior of the summons is still exponential because there's a 2 raised to minus n essentially running through the summons. But you have this additional factor, right, which alternates between 2 raised to 1 and 2 raised to minus 1, right? So you are basically multiplying the 2 raised to minus n type exponential decay with an alternative factor of plus 2 or plus half, right? So you kind of have this oscillatory half and 2 multiplication that you are riding on top of the exponential. And you can see that something like the ratio test would in fact get stumped by this, because whenever you multiply these successive entries of the summands either by half or 2, well, their ratio is going to basically jump by a factor of 4, right? And that would change. It would go up by a factor of 4 in one case and go down by a factor in the next case. And so that's going to give you a 16 factor difference between something like xn plus 1 by xn, which is going to stump the ratio test. But the root test is fine, because when you take the nth root of all of this stuff, the prefactor where you multiply by 2 or half will wash away, and so the root test will work. So specifically, if you look at the ratio, so root test works. I leave that for you to check. In this case, alpha is equal to half. Okay, so you will in fact have absolute convergence. Right, but if you look at the ratio test, right, to look at the ratio test, you need to look at essentially the ratio of xn plus 1 by xn. Let's call this xn, of course. Then if you look at xn plus 1 by xn, well, it turns out that you have to take multiple different cases based on whether n is even or n is odd. So again, I leave you to make the exact computation on your own, but it turns out that if n is even, you will get this ratio to be 1 by 8, whereas if n is odd, you will get this ratio to be 2, right? So clearly, I mean, those factors have been engineered in such a way that I get numbers on either side of 1, right? Now that I have this, well, it's clear that the lim inf of mod xn plus 1 by xn would in fact be 1 by 8. The lim sup of the same sequence would be 2, because they are on either side of 1. The ratio test would be inconclusive. Right? And that kind of demonstrates why the root test is in fact strictly stronger than the ratio test. Maybe I'll do one final example, and this final example is in fact goes back to the definition of E, which we did in the previous video, where you're looking at something like summation 1 by n factorial. Okay, so in this case, it's actually, at one level, it's easier to apply the ratio test. So we already know this fellow converges, right? That's already been done. We proved using a direct application of the comparison test that E is well defined, and so the series in fact does converge, right? This is exactly what we called E. Okay, now let's apply the ratio test. Let's define the summands to be xn. In this case, xn plus 1 by xn is equal to, well, 1 by n plus 1, which tends to 0, which implies that the series converges absolutely. So this is one example of a of a series where the summands in fact don't behave exponentially, but in this case they actually decay faster than exponentially, right? Which is also where the ratio and the root test work. So the ratio test trivially shows that this fellow converges. I leave it to you to apply the root test.
I found this on the web for where is the summands in fact don't behave faster than exponent.
Oops, sorry about that. Yeah, so I leave it to you to apply the root test in this case to show that the same series actually does converge, right? Now, because I told you that the root test is more powerful than the ratio test, the root test should also take you to the same conclusion. All right, so with this we'll stop. There is one more test for convergence of series to consider, which we'll do in the next video.